All right, chemistry students, we're going to be continuing our talk on chemical reactions. Last lecture we did synthesis and decomposition. This lecture is going to focus on single displacements. Again, the same sort of setup that we're used to from the last bunch of lectures. Up here I've got the note that you got on your D2L page. And here I'm going to write down the little things that will help you out and give you some examples on the whiteboard here. All right. If you want to write these down in your notes, don't forget, this is a YouTube video. You can always pause it and write down the things that I'm writing if I write a diagram or an equation or something like that. All right? So single displacement, every single teenage drama show you ever watched on TV have something in common. So let's go through and see why that is. So a single displacement reaction occurs when you have a single element, one single element, and it goes up to a compound, which we know is at least two elements, and takes the place of one of the elements in that compound. So what basically happens is this. See that? Very quick, right? Like a magician. The single element comes up, boom, and takes one of the elements out of the compound and is now partnered with it. All right? So the reason I say it's like those teenage dramas is because we see that all the time on TV in those shows, right? You've got this couple, they're together, right? They're in love, they're the, prom king and queen, and then of course what happens? Moody Drifter Kid moves into town. Here's Moody Drifter Kid. They move into town, and what happens? Of course, someone in that couple ends up going with Moody Drifter Kid. The prom king and queen, they break up, and whoever's on the outside, this person right here, is left to quietly plot their revenge for the next 11 episodes of the season. And this is exactly what a single displacement reaction is. This is my compound. This is my lone element. And what happens is this lone element comes in and tries to take one of these things to the compound and take its place. And so now the lone element is part of the compound, and somebody that was in the compound is now kicked out and left to themselves. So let's take a look at some of the information that we have. So it's also known as a single replacement. If you're out there looking at extra materials online, you'll see single replacement, single displacement. It means the same thing. The general equation again is A and B, that's our couple. Z is our Moody Drifter, our lone element. And of course, Z pops in there, kicks out A. A is left quietly plotting its revenge, and now these two are going out together and everything's great, or so it seems. Right? The one thing we have to remember, in this equation, we see A and Z switch places. So if Z is a metal, that means it takes out the other metal and switches places with it. You can't have a metal switch with a non-metal. All right? So the metal kicked out the metal. Here's the metal that got kicked out, and here's the metal that took its place. So metals displace or replace metals, and non-metals displace or replace non-metals. All right? So the pattern that we look for is the single mysterious Moody Drifter loner kid moves into town and breaks up the happy couple. Here's our happy couple. Here's that lonely Moody Drifter kid right here, right? So mysterious, this kid. And of course, someone falls in love with him and breaks up their couple. Anyway, here are some examples here down in the corner. You can see iron is by itself. And here's copper 2 sulfate, and iron kicks out the copper. Metal takes out metal. And now iron is with the sulfate instead of copper. In the second example, potassium kicks out magnesium. This is a metal. It kicks out the other metal. Now potassium is with oxygen, and the magnesium is left on its own. In our last example, we have our couple is copper 1, and it's with fluorine. So we have copper 1 fluoride and barium together, and barium moves into town, and barium takes the place of the copper and kicks it out, and we have barium fluoride now. So Pretty simple, right? But not so fast, right? Not everything works out nice and crisp and clean like that. Sometimes the moody drifter kid moves into town and the couple tells him, hey, get lost. We're in love. We're staying together. You get out of here, right? So how do you know when the moody drifter kid can break up the couple and when it can't? Well, there are rules, right? There's a thing called the activity series, and the activity series is like the pecking order of who can displace the other person, right? It's like listing who's stronger than the other person, who's stronger than each other. So here's our activity series. Now, you do not have to memorize this list of elements, all right? I'm going to move the iPad after a bit, and I'll write it up at the top of the board, but it's in your notes here if you've been downloading the stuff from D2L. This is on D2L. But the way it works is the things over here at this end, the left side of it, like lithium and potassium and barium, these are the strongest. And then we have mercury, gold, or silver and gold. These are the weakest. So these things are very tough to displace. These things are very weak and can easily be kicked out or displaced. So the further you are to the left, the stronger you are. The more to the right you are, the weaker you are. All right? So you can only be displaced by something that is to the left of you. So if we took something like zinc, which is right here, zinc can be kicked out by calcium. Zinc could be kicked out by lithium or magnesium or any of these elements over here. Zinc will not get kicked out by any of these elements, so. So if zinc is in a compound and nickel comes along, nothing's going to happen. There'll be no reaction. Nickel can't break zinc up. If lead comes along, it can't break zinc up if it's in a compound. So that's kind of how it works. You can only be kicked out or taken out of a compound by something to the left of you. There's also a halogen, that's group 17 on the periodic table. If I bring up the periodic table, the halogens are all right here, right? And this one actually works very, very simply. The top element, fluorine, is the strongest. And as you go down the column, it gets weaker and weaker. So it's the same thing. Fluorine is the strongest. Iodine is the weakest. So that's these elements right here. So using the activity series, there's 3 types of single displacement reactions that we're going to be using this with. There are the straightforward type of single displacements. Then there are reactions with acids and reactions with water. And I've summarized them all here. So when we have a straightforward single displacement where a metal's trying to take out a metal or a non-metal's trying to kick out another non-metal from a couple, we use the rule of who's to the left, who is stronger, right? So we use the activity series just like we outlined it just before. There are reactions with acids. Now, every acid has hydrogen. And if you notice in your activity series earlier, hydrogen was in there with all those metals. And the reason it is that hydrogen is that weird sort of nonmetal that isn't a negatively charged ion. Hydrogen forms a positive ion. Just like all the metals form positive ions, that's why it's in that table. The positive ion tries to take out another positive ion. And then reactions with water, only the first 5 elements are going to be reacting with water. None of the other ones. So lithium, potassium, those guys, those first 5 at that end, they will react with water. All right? When it does, if there is a reaction, what will form is a hydroxide of some sort and hydrogen gas. So we'll come back to that in a second. So I am going to leave this. Our next lecture will be on double displacements, but I'm going to move that. And what I'm going to do is I'm quickly going to write the activity series across the top of my board. All right? So let's get a good color here that will show up. And I'll see if I can squeeze it all in the first try. So LIKBACANAMGALZNA N-F-E-N-I-S-N. I think we're going to make it. P-B. H. Gonna be tight, gonna be tight. C-U-H-G-A-G-A-U. Whew. Just got that in. All right. So here's my activity series. You'll notice that I wrote the hydrogen, right? The one non-metal here, I wrote it in red, and I'll tell you why in a little bit. I'm also going to put a wavy line underneath of those first 5 elements: lithium, potassium, barium, calcium, sodium. All right? So there's my activity series. We know that this end down here, this is strong. These guys, they'll steal your girlfriend or boyfriend, no problem. These guys up here, they're pretty weak. They're not stealing your boyfriend or girlfriend. All right, so the first type of reaction, single displacement reaction that we're going to do is the straightforward type. And I'll do several examples of each, right? So the first ones are straightforward. Our first example is going to be calcium plus copper 1 sulfide. And that's what we'll start out with. So I want to see if a reaction is going to occur here. So I find copper. Here's copper right here, right? Copper's right here. So I always start with the one that's in the couple. Here's my couple here, my compound. There's copper. I find copper. Then I find the other one. Calcium wants to break up that couple. Calcium is here. So calcium is stronger than copper. So there will be a reaction here. This calcium is strong enough to take out this copper and kick it out of the compound. So this is stronger. It can kick this one out, and that's what will happen. So the Ca goes with S, and these are both 2s. That's 2 plus and 2 minus, so that's a good formula. And copper is left by itself. And any metal by itself is by itself. I have 2 coppers there. I do not put a 2 here, right? I don't do this. It's not a diatomic gas. One of the rules of Fight Club is any metal by itself stays by itself. We can always balance it with coefficients. So if we look here, copper was weaker, calcium was stronger. Calcium comes in, bumps copper out. It now goes out with sulfur, and copper is left to quietly plot its revenge. So the next thing that we have to do is balance this equation. So 1 calcium goes in, 1 calcium comes out. So far, so good. 2 coppers went in. I've only got 1 here. So 2 goes there. Remember, do not balance by altering subscripts. That'll only get you killed. So calcium, calcium, 2 Cu, 2 Cus, sulfur, and sulfur. So that one's good just like that. All right. Our second example, NaCl plus, we'll go with nickel. Now nickel's shifty, so we'll say we have nickel 2. All right. So we get this. Here's our couple. Here's our moody drifter, right? It's got a charge of 2 plus. So what do we start with? We start with whoever is in the couple first. So if I do that, I can see that sodium is right here. Then I find the person that wants to break them up, nickel. So sodium is here, nickel is here. Well, sodium is stronger. So when nickel moves into town, sodium chloride's going to say, get lost, moody drifter kid. We're in love, we're staying together. So this is not strong enough to bump this out. Na is strong and it's already in the couple. So what happens is no reaction occurs. Nothing. If I have a solution of sodium chloride and I drop nickel in there, it'll just go bloop and drop to the bottom of the beaker or the vessel, whatever I am doing the reaction in. Nothing will happen. It's like dropping a penny into a glass of water. It'll just sink down to the bottom. So no reaction takes place here because this is not strong enough to bump that out. Reaction number 3. Magnesium plus will go lead 4 oxide. Will there be a reaction here? Again, here's my couple. There's lead. Here's the moody drifter that comes into town, wants to break them up. And it's over here. It's at the stronger side. Magnesium is stronger than lead. So magnesium will kick this lead out. So magnesium now goes with oxygen. This is a 2 and that's a 2. So this is a good formula. The 2 2s will cancel. And lead is left on its own. And I'm fine with it being on its own. Any metal by itself stays that way. I don't put a 2 or 3 there. It's just Pb. So now I have to balance this out. 1 magnesium, so far so good. 1 lead, so far so good. But the oxygens are going to give us the trouble here. So 2 O's and only 1 come out. I can't put a little 2 there, that'll get me killed, so I got to put a big 2 there. And again, whenever I put a coefficient in, I start at the beginning. Because fixing one thing can sometimes lead to something else being put out of whack and not balancing anymore, like our magnesiums here. So now we have 1 magnesium going in, and now there's 2 coming out. So I put a 2 there and we'll see. 2 magnesium, lead, 2 oxygens, 2 oxygens. So that one's balanced. Our last example of the straightforward type is going to be calcium fluoride plus fluorine gas, which is diatomic. It's one of those diatomic gases. Whoa, gave away the secret ending beforehand. Anyway, so we look here. Here's our couple. This is our moody drifter, but our moody drifter is not one of the metals that we see up here. This moody drifter is one of our non-metals. So I get out my periodic table and I know with these non-metals, these halogens, I've got chlorine, which is right here, and fluorine, which is just above it. And I know the strongest ones are at the top. So fluorine is stronger than chlorine. Remember, the order was like this, F, Cl, Bri. The same order going down this column, F, Cl, Bri. All right? So, Cl is in my couple, and F is the moody drifter. F will be able to kick out Cl, so I'll get CaF2, and that will kick out the chlorine. And chlorine we know is diatomic. It's a diatomic gas. If we go to balance it, we have 1 calcium in, 1 calcium out, 2 chlorines in, 2 chlorines out, 2 fluorines going in, 2 fluorines going out. This one is already balanced. We said that would happen sometimes in previous lectures. We said, you know, sometimes you do the formulas right, it already balances. This one is one of those. So these are some examples of straightforward single displacements. So let's try a few now with the acids. I'll erase this again. You can simply pause the video if you wanted to write those down. But I'm going to keep moving. Clean my board. So the next one. Single displacement reactions with acids. Now we know that every acid starts with hydrogen, right? And you'll notice that we wrote the hydrogen in red right here. I write the hydrogen in red because acids turn litmus paper red, and it makes that hydrogen stand out, right? It reminds me, acids turn litmus red. Here's that red H. When I react something with an acid, this is what I got to pay attention to. So we'll do a few examples here. Our first example, we'll take sulfuric acid and we'll drop in some potassium. All right. I'll get rid of this now that we know all acids begin with H. We knew that beforehand anyway when we did names and formulas. So K wants to kick out the H here. We can see K is here, H is here. So we start here with all the acids. Start with your couple. Right here, we've got a sulfate ion and hydrogen. So that's my couple. Hydrogen is here. Now find the Moody drifter. K is right here. K is one of the strongest. So K is going to be able to kick out that hydrogen. So we're going to get K2SO4. Remember, this is a 2. That comes down. This is a 1. We don't show it. Names and formulas are still key, people. And hydrogen gas will be released. When we go to balance this, 2 H's, 2 H's, a sulfate and a sulfate. And then the K's look like they will have to be fixed. 1 K going in, 2 coming out. So I'm going to pop in a 2 right there. And then we're balanced. All right? So again, my acid had the hydrogen in it. K is here. It is much, much stronger. So the K bumps it out. Metals form positive ions. So does hydrogen. So positive kicks out positive here. The hydrogen acts like a metal. It's up here with all of these metals. Number 2, hydrochloric acid, one of our binary acids, and barium. That didn't come out too well. There we go, barium. And we'll mix those together. So if we drop some barium in with some hydrochloric acid, what will happen? Again, my acid starts with H. Here's hydrogen here. Barium also is very strong. So barium will be strong enough to kick out that hydrogen. So we get BaCl2, and of course hydrogen is diatomic when it's by itself, and we have to balance this. So 1Ba, 1Ba, here's where we're going to have an issue right here. 1 hydrogen goes in, 2 hydrogens come out, so I will put a 2 here, 2 hydrogens, 2 hydrogens, 2 chlorine, 2 chlorine, and then like we said before, the BAs will cancel. So this is now balanced perfectly. Reaction number 3. So this time we've got H3PO4, which is phosphoric acid, and we drop some silver into that acid. So again, I start with my couple. Here's hydrogen, and silver wants to kick it out. The only thing is silver is right here. So hydrogen is already in a couple, and silver's trying to kick it out. It's not strong enough. Silver is one of the weakest ones. So here there will be no reaction. This Rx is my shorthand. I think a lot of people's shorthand for reaction. So if you write no Rx, I'll know what you're talking about. It means no reaction. All right? So those are some examples there, some reactions that will proceed and one that doesn't. And again, you're just using the activity series and the H for the acids, because all acids begin with hydrogen. You can pause the video if you wanted to write those down, but I know I'm going to go forward here because you can do that. And our last group are reactions with water. So reactions with water. So when you were a kid and you were drawing water, you're drawing the ocean, you probably did this, right? So that was water in your pictures when you're in elementary school, right? And that's why I drew this wavy line underneath of the first 5. Only the first 5 will react with water. So when I take the first 5 elements here, lithium, potassium, barium, calcium, and sodium, and I do that blue wavy line, it reminds me of water. And they are the only 5 that will react with water. And what they'll form is a hydroxide, so something that ends with OH, right? Hydroxide is this thing, as a 1- charge for when I'm making up formulas, and hydrogen gas, which we know is a diatomic gas. So we'll end up with something, hydroxide and hydrogen gas as my 2 products if there is going to be a reaction. So let's take a look at some. our first reaction. We take zinc and we drop it into some water. If I take zinc and I drop it into water, I find my zinc, and zinc is right here. And zinc is not part of this wavy line. It's not part of the first 5. So that zinc is just going to drop to the bottom of the test tube or the beaker or whatever it is, and there'd be no reaction. Only the first 5 will. There's my Rx for reaction again. So nothing happens here. It'll be dropping like dropping a quarter into a bucket of water. It's just going to sink down to the bottom, right? Reaction number 2. If I take lithium and I add it to water, what would happen then? Well, I got to see. Here's lithium. It's one of the strongest elements, and it is covered by our wavy line. So lithium will react with water. So those 2 products that we said we would get, one is a hydroxide. So lithium hydroxide will form. Lithium has a charge of 1. Hydroxide has a charge of 1. So that's good. Those 2 ones cancel. There's a good formula. And of course, hydrogen gas. So that's my reaction. I'll now try to balance this. So I'll look, lithium, 1 goes in, 1 comes out. Everything's great. 2 hydrogens go in, and I got 1 here and 2 here. Now I know whatever number I put here, 2 times whatever number is going to be even. This is even, but this 1 by itself is making it odd. So I'm going to double this up. So I'm going to put a 2 here. That will make 2 plus 2, which is 4, and then I can put a 2 here. 2 times 2 is 4. Again with the hydrogens, 2 times 2 is 4 hydrogens going in. 2 hydrogens plus another 2 is 4 coming out, so that's good. And again, we always start at the beginning and double check. 1 lithium in, now there's 2. So I got to fix that. Sometimes fixing something throws something else that was already good out of whack. In that case it did, but we caught it. All right, so that reaction is good. If we look, 2 lithiums, 2 lithiums, 2 times 2 is 4 hydrogens, 2 plus another 2 is 4 hydrogens, and then 2 oxygens and 2 oxygens, so everything is great. The last example, we take barium and we add that to water. So again, for water, we know the rule is only the first 5 will react. There's barium there. It's right in the middle of those first 5, so there will be a reaction here. We will get barium hydroxide and hydrogen gas. And of course, we have to balance this. So barium and barium, good. 2 H's. 2 H's plus another 2 is 4. So 2 times 2 is 4 H's. Start again. Ba, Ba. 2 times 2 is 4 hydrogens. 2 hydrogens plus another 2 is 4. 2 O's and 2 O's. Whatever's in those brackets, I got 2 of them. So 2 O's and 2 O's. So that one's done. All right, so those are some good examples of all of the different types of single displacement reactions that we're going to be covering in our course. If you go to the D2L page shortly, I haven't listed it yet, but I will. There'll be a worksheet there called singles and doubles. The single displacement side of that sheet you can do. Hold off on the double displacements. We will get to those in the next lecture, but do the single displacement side of that sheet now. You're fully equipped to do it. What you're going to do is you're going to be given reactants. You will form the products, and then you'll balance the whole thing out if need be. Anyway, hope everything was crystal clear. If not, throw some comments in the YouTube channel, or even better, go to Edsby and throw in a question or comment there, and I can get back to you as quickly as possible. Anyway, have a great day, and that's it. All right, thanks.